In this portion of the video, we will be discussing Brownian motion. This is the kind of motion observed by Robert Brown in 1827 when he looked under a microscope at a pollen grain suspended in water and noticed that it jitters about, it doesn't stay still, and he originally thought that the pollen was a living thing due to this, but afterwards he looked at various inert objects such as ground up sand under the same conditions and saw that they jitter about as well. This got buried in the literature and in 1905 Einstein picked it up and he characterized it mathematically, and from this derived what's now known as Avogadro's number. And later this was confirmed by Perrin in 1908, for which Perrin was awarded the Nobel Prize, Einstein having been awarded it 5 years before Perrin was. The underlying purpose and drive to understanding Brownian motion for Einstein was to prove the existence of atoms, and he felt that if he could prove that these small particles are driven by yet smaller particles to move around a bit, then he could prove the existence of these yet smaller objects that were beyond our capability to observe through microscopes. So he accepted Maxwell-Boltzmann's statistics and molecular kinetic theory of heat, and he then used Van Hoff's law of dilute solutions and osmotic pressure and analyzed these and calculated the molecular dimensions of these dissolved molecules. And using these equations, he then derived the formula that we have on the board. This formula describes the so-called mean square displacement. That is, it's the mean, the average, that's what the angled brackets mean, it's the average, and x squared is the square displacement. So it's the square of the displacement. So the average of the displacement squared. So you square the displacement and then take the average. So, and then R is the gas constant, T is the absolute temperature in Kelvin, eta, that's the N with the little thing hanging down below it, that is the viscosity. So eta, the N with the thing hanging below it, that's the viscosity. Na is Avogadro's number, R is the radius of the particle, and tau is the time between your observation. So your initial observation when you start the particle, that's the large one that we saw in the last slide, to your second observation.
This is about the photoelectric effect. So the photoelectric effect is what occurs when you have two plates that are made out of metal, and light hits one plate, and then electricity flows. So I'm going to write that as electrons flowing down. And the way that this has to happen if electrons are flowing down this way is electrons must be jumping from this electrical metal plate to that metal plate. Okay, so you've got electrons jumping due to this light hitting the metal surface and causing electric current. So first, again, we're going to talk about the classical way that this would be understood and how that would result, and the quantum mechanical result, which actually explains the experiment. Okay, so the idea from classical mechanics is that, again, since you have this metal plate and you have light hitting it, that if the light is more intense, then it's going to cause more electrons to jump with greater velocity or speed. And the reason that they would give for this is that that when the light hits the metal surface, if it is intense enough, regardless of what its frequency is, if it's intense enough, it will jostle the electrons and make them shift around in sympathy with the light wave. And when this happens, it will cause the electrons to jump out of this plate and into this second plate. And the greater the intensity, the more often this will happen. And again, there's no dependence on frequency. The problem with this is that didn't happen. So there's two fundamental errors that this makes if you look at the graph that experiment would give you. So experiment would show something like this. You have the kinetic energy of these electrons, so their kinetic energy versus the energy of the incoming light. So we'll call that nu, or the frequency, sometimes called F, but we'll call it nu. So what it will look like is this. It's a straight line, okay, that intersects and ends at the x-axis. So there's some minimum energy that's required, or some minimum frequency, oftentimes referred to as the work function. So every metal has a particular frequency, and any light hitting that metal below that frequency will not eject electrons. Any light, regardless of its intensity, will eject electrons if it's above this frequency. So there were two errors in this classical mechanics thinking. The first is that from this graph you can see that not all light will cause electrons to jump from one metal plate to the other. The second is that there is no dependence on the intensity when it comes to the kinetic energy of these electrons. So how did Planck and Einstein in particular resolve this? Well, they assumed that energy is quantized. So they assumed that this energy is equal to h nu, where h is Planck's constant, is that same constant that fits the black body radiation curve. And at the time, Planck thought it was just a curiosity, doesn't really mean anything physical as far as he was concerned, but Einstein was thinking, no, this actually does have some real meaning. So h times nu is the energy, and if you think of the kinetic energy as whatever is left over when the light, so basically the light's energy goes into one of two places. It either goes towards making the kinetic energy larger, or it goes towards ejecting the electron in the first place. So the idea is that you need some minimum energy to eject the electron, and then any excess energy above that goes towards the kinetic energy. And that was the central result of Einstein's paper.